In this video, we will talk about regression. Regression is a way of statistical analysis in which statistical relationships are seen as predictions. So trying to predict or estimate values for one variable based on values for another variable or more than one other variables. This is a numerical calculation, involves numbers. So it is meant for quantitative variables. However, there are actually tricks that are called contrast coding that can be used so that regression is actually possible also with categorical variables. This is not something that we will see in this course. In fact, there are many different varieties of regression. They're all based on the same concepts, but the mathematics become quite complicated very quickly. So we'll only look at the very simplest case, which is called simple linear regression, so that we understand the concept and then are able to read a table of results. So the main idea behind regression is what is called a linear model. A linear model involves two numeric variables, and there are only two in our case of simple linear regression. There can be many more in general, but here we're only considering simple linear regression. So there are just two numeric variables in our linear model, and we're going to have one dependent variable called y for our purposes here, and one independent variable called x. So we'll be trying to predict y from x. We want specifically to estimate the values of y from the values of x. So if we had x being somebody's age, a child's age, and y being the same child's vocabulary, this amounts to trying to estimate or predict a child's vocabulary from their age. In general, our prediction is made using a formula like this one. This formula has two parameters, alpha and beta. So these two numbers, we want to find two numbers so that we will be multiplying one number with x, with our own variable, adding the other number to it, and this result would be our estimate, our prediction for y, for the other variable. Y hat is our estimate for y. And of course, we will not predict perfectly, so y hat will in general not be equal to y. We will make some error. There will be some difference. The difference between the actual value of y and our estimated, our predicted value for y, the difference between these two is our prediction error, which in regression is called residual. And we use the Greek letter epsilon to indicate the error. So the point of this analysis is to find alpha and beta here so that the prediction error will be as small as possible. We will minimize the residual. Let's see in an example what this means and how it might work. These are data for about 600 children with their age in months and vocabulary indicated in the scatter plot. So let's say we're interested in predicting vocabulary from age. So vocabulary here on the vertical axis will be our dependent variable, and age on the horizontal axis will be our independent variable. What is our predicted vocabulary for children of age 4, so 48 months? If a child is 48 months, what do we predict their vocabulary to be? These are children around 48 months of age, and these are their actual vocabulary scores. As you see, they occupy a substantial range. What is our best guess for vocabulary for these children? Well, it's the mean of these data points. Our best guess for a range of values is the mean because the mean is the value that minimizes the squared error. So the mean for these displayed data points is here, and the green line here on top of it is the standard deviation. So this is expected to include about 2/3 of children within one standard deviation. What is our prediction for children of age 50 months? Well, these are the children around 50 months, and this is the mean for all these points. And then these are the data points for age about 52 months. And if we keep doing that for each age, we come up with a mean, which is our best guess for that age, and a corresponding standard deviation, which is an estimate of how far off we can expect to be. Now, this looks like a linear relationship on the scatter plot, and indeed, if you see, all the means are approximately lying around a straight line. We can draw a straight line that goes near the means. And the whole point of linear regression is trying to find this line and use this line to predict vocabulary from age instead of using the means of individual ages. Why do we want to use this line? Well, the means for specific ages are actually quite unstable because there's only a few children at each age. So these are basically very small samples. And estimating a mean from a small sample is okay, but as we know, this is going to be a very noisy mean. Small samples are quite likely to be unrepresentative in comparison with larger samples. So as you see, some of these means go a bit up, some go down, some have larger standard deviations that indicate much lower confidence in our prediction. So in general, these individual means are not a very good idea. Moreover, in a real data set, we might have missing data for some ages or much fewer data. That would make it very difficult to predict. But if the relationship is in fact linear, if we can make the assumption of linearity, then this entire red line can be found on the basis of all the data points considered together. So this is a much more reliable way to come up with a best guess for predicting vocabulary from age that is not subject to the unreliability and instability of individual means at each data point. So we don't want to have to calculate and use these means. We want to calculate a single line instead that will do the job much better. To see how this line can be calculated and what that means, it's best to switch to an artificial example with fewer data points where we can see everything more easily. So let us leave our prediction of vocabulary by age for now and switch to this artificial data set with just 10 data points. We still want to predict y from x. So we want to predict the value around 5 from x equals 2, for example, for this point, and similarly for each data point. Which line is the best line for this prediction? Is this a good prediction line? Or is this a good prediction line? Maybe this one. How can we find out? Well, the best line is by definition the one that makes the least amount of error. So to find the best line, we have to look at the errors. These are the distances between the points, the data points we actually have, and the predicted values that correspond to them. Note that these are all vertical from the line because they're the differences between a predicted and an actual data point. So for this particular line, if we have x equals 2, the actual value of the data point is near 5, but the predicted value on the green line here is about 4. So this is how much we are off. This is our error for x equals 2. We see that the error for x equals 4 is much larger. And sometimes we predict a higher value than actually is the case. So here the error is going downwards. So we over predict for x equals 3, but under predict for x equals 4. For this particular line of prediction, these yellow lines are the prediction errors or the residuals. These are the actual values, so we can see how much they are numerically. You see that when the points lie below the line, the residuals are negative. When the points lie above the prediction line, the residuals are positive. And here we can make a table. In the first row, we see the actual values of our data points. These are our measured values for y. On the second row, these are the predicted values, so the estimates based on this green line. For this particular line, these are our estimates for y. And the difference between the actual and the estimated values is the error or the residual for each data point. So the difference between these two numbers is this. And the difference between these two numbers is this, and so on. These are all the residuals. And as you should probably have guessed by now, because we have a bunch of differences, some of which are positive and some of which are negative, what we're going to do next is to multiply all the residuals by themselves. So these are the squared errors. And we can add all these up to come up with a summed squared error, which for this particular line is equal to 130.9. So this is the sum of all the squared differences between the actual value and the predicted value. That's our sum squared error. For each line that can be drawn, for all possible lines, we have a corresponding set of residuals and therefore a sum squared error. So for this line, the squared error is 153. For this line, it is 163.2. If we could draw all the possible lines, calculate the squared errors, and find the one with the smallest sum, that would be our perfect line. In practice, there are formulas that we can use to calculate the optimal line very quickly without having to try a large number of different potential candidates. So as it turns out, this is the best line for predicting these y values from these x values. And this particular line is defined by two numbers. The first number that is used to define this line is called the intercept. The intercept is our predicted value when x equals 0. So when x equals 0, although we have no data points there, it doesn't matter because the line just extends as much as we want all the way to minus infinity. So 0 is always somewhere, and our predicted value for x equals 0, in this case, is minus 0.84. Where the prediction line hits the x equals 0 line, that's our intercept. And the second number that we use to define this line is called the slope. The slope has to do with how much the line rises when x increases. Let's look at this visually. So if x goes from 1 to 2, that's a difference of 1. X increases by 1 between this line and this line. For x equals 1, our predicted value of y is here, and that is 1.43. and for x equals 2, our predicted value for y is right here, and that's 3.7. The difference between these two predicted values of y is 2.27. That is, the difference in predicted y when x increases by 1 is 2.27. This is called the slope, and because this is a straight line, the slope is the same everywhere. So it could have done this somewhere else. For example, we could have done it here. X equals 6 is this line, and 7 is this line. So these two lines are 1 unit apart. Our predicted y for x equals 6 is 12.8. Our predicted y for x equals 7 is 15 point something. And the difference between these two values is, no surprise, 2.27. No matter where we do this, a unit increase of x is accompanied by an increase of 2.27 in y. So that's how fast the line is rising, or how much the line is sloping, the slope. If you have a point as the intercept and the rate of rise as the slope, then the line is fully defined. And this is the line we use to predict y from x. An important property of this line is that the predicted value when x is the mean of all our x values, the predicted value of y is actually the mean of all our y values. So the lines of the two means for the x and y variable, these are the lines of the means, and they meet on this prediction line. This is an important property of this line. The line is called a regression line. And this is a line that we can use to predict one variable from the other. This is not reversible. This line that we showed only predicts y from x. And that's because our residuals were calculated vertically. If we wanted to predict x from y, we would come up with a different line, which would result from calculating residuals on the x direction. And that would lead us to a different line having the minimal sum of squares, sum of squared errors. So the regression line is a line that predicts one specific variable from another specific variable. It is the line that minimizes the prediction error. Actually, it minimizes the sum of squared residuals, because prediction errors are called residuals in statistics. It means what is left over after you have predicted what is the part that you haven't managed to predict. The intercept of the line, one of the two numbers that define the line, is the predicted value of y for x equals 0. This is always what the intercept is, whether or not 0 is actually a plausible value for x. So in terms of the numbers, intercept is always the predicted y for x equals 0. And the slope of the line, the other number that defines it, is always how much y changes when x increases by 1. How much our estimate of y changes when x increases by 1. These are the definitions of intercept and slope. And always the predicted value for x equal to its mean is the mean of y. So the mean predicts the mean. These are the properties of the regression line. And this is the formula of the regression line. This represents the line of prediction that we just showed. Sometimes there are different symbols used, slightly different, such that instead of alpha here, we see beta 0. And instead of beta, we see beta 1. This is possible to see in some textbooks. These are commonly used symbols as well. However, it is represented, this part is the intercept, the part that is just added, and this part, which is multiplied by x, is the slope. So the slope is the number that is multiplied by our independent variable, and the intercept is the value that is added to that. The intercept and slope are actually derived by formulas, which for the simple case that we're examining, simple linear regression, are these ones. This is the formula for beta, and this is the formula for alpha. I do not want you to try and learn these formulas, but you can just look at them now and see that this reminds us of something that we've seen elsewhere. So the sum of the products of the differences of the two variables from their means may remind you of the correlation. And in fact, the beta of simple linear regression is equal to the correlation between the two variables multiplied by the ratio of their standard deviations. You don't need to remember this, but it's good to have in mind that correlation and regression are very closely related. As for the intercept, alpha is given by the relationship between the means, as we said, that mean x predicts means y. And so once you calculate beta, essentially based on the correlation, you can calculate alpha by bringing in the means. In practice, you will just see these calculated by your statistics program. Now let us go back to our scatter plot and see what this implies for the variances. Because what regression does is predict one variable from another, and in this way account for a part of its variance. Let's see what that means. This is the mean of y. The mean value for the y variable is this line. And therefore, these orange lines are the distances between the data points and their mean on the y. These are the deviations. These deviations of the data points from their mean can be used to calculate their variance. So this is the variance of y. It is the sum of the square deviations, the distances of the points from the mean, divided by n minus 1, one less than how many they are. This is the formula for the variance. And if you add a square root to it, it will become the formula for the standard deviation. So this is how much variability there is in our dependent variable. Let's add the regression line. Now, our actual y values, our data points, are this distance from the prediction line. And as we said, these are the residuals. The residuals have a mean of 0, and this is their variance. So the difference of the actual data points minus their predicted values squared and divided by n minus 1, this is the variance of the residuals. This is how much variability remains in the data after we have predicted them, after we have guessed a value in each case. This is the leftover variability. And the third part is the distance between the mean value of y and the predicted value for y based on x. The green lines are the part of the variability in y that we can account for by x. And as these are deviations of a sort, the deviation between the prediction, the regression line, and the mean for the dependent variable, this is also a variance. This is a variance that we can account for. So of all the variability in our dependent variable, which is expressed in its variance here, the orange lines, we can account for a part, which is the green lines, and there is a leftover part, which is the variability of the residuals. If you look at each data point, for example, this one, its total distance from its own mean, so this is the orange line, the distance of this data point from the mean of all y. This distance is broken down into two parts. One part is the green line, which is how far from the mean our prediction is. And the other part is the red line, which is the residual, how far from the prediction the data point is. And you can see that the orange line is basically made up of these two parts, a predicted part and an unpredicted part. The interesting thing here is that the same additive relationship holds for the variances. So we can break down the total variance for y into two parts. A variance that is left over, the residual variance that we're not explaining, and a variance that is what we account for by considering x. So knowing x takes this much variability out of y. It's like the variability of y that was initially unexplained, just variability, dispersion around the mean. And then once you bring x into the picture, it turns out that a chunk of that variability is actually possible to account for, is explained in a sense by x. So there is a proportion of this total y variance that is accounted for by the regression. Looking at variances this way, it is also possible to form an F ratio and examine whether our prediction is statistically significant in terms of reducing the error variance. If you remember how we did an F ratio for the analysis of variance. But that's not what we're going to do here, as we will focus on the significance of the individual statistics. For now, let us just keep from this that the variance accounted for plus the residual variance equals the total variance. The variance accounted for is the part of the total variance that can be predicted by our independent variable using the regression line. The residual or error variance is the part of the total variance that is left unaccounted for, at least unaccounted for by this one independent variable. And the proportion of the total variance of the dependent variable that is accounted for by the independent variable in this way is called the coefficient of determination. It is usually represented like this with a capital R square. And as it turns out, it is equal to the square of the correlation between x and y for this simple case of simple linear regression with just one independent variable. So the coefficient of determination, that is the proportion of variance in the dependent variable that we account for by the independent variable, is equal to the square of the correlation between these two variables. If we run this regression analysis in a statistical program, we will get an output like this. And in this output, we have an estimate for each statistic. So the intercept and the slope for our independent variable. And our intercept is minus 0.84, as we've seen, and the slope is 2.27. And as for every other statistic, we get a standard error for each one of them. This is the standard error for the intercept, and this is the standard error for the slope. We will not consider the formulas that provide these standard errors. Then if we divide each estimate by its own standard error, what we are actually doing is running an one sample t-test against 0. So this divided by this produces this t-value, and this divided by this produces another t-value. A statistic divided by its own standard error is a one sample t-test against 0. This is like when we had a paired values t-test, where we divided the difference by its own standard error, and we got a t for the difference as a test against the null hypothesis that the difference was 0. This is the same thing we're doing here. So this is the t for the intercept, and the null hypothesis is that the intercept is 0. And this is a t for the test of the hypothesis that the slope is not 0. The null hypothesis for the slope is that the slope is equal to 0. And this is the t-value for the one sample test that tests this hypothesis. The degrees of freedom here are n minus 2, so 2 fewer than the number of entities or the number of data points on each variable. You can think of it as because 2 means are involved. Actually, it has to do with the number of lines on this table here, but it's the same either way. And so if you look up these t-values for n minus 2 degrees of freedom, we see that the p-value for the intercept is very high. So we cannot reject the null hypothesis that the intercept equals 0. But the p-value for the slope is very small, is below the conventional limit of 0.05. And so we can reject the null hypothesis that the slope is 0. In general, we don't care about the intercept. The intercept is necessary for finding the best prediction line. The intercept is one of the two values that define the regression line. So it's necessary to compute, but we don't care if it is statistically significantly different from 0 or not. What we do care about is whether the slope is statistically different from 0. So a statistically significant slope tells us that x is a significant predictor of y, that by using x, we can reduce the variance in y by a statistically significant proportion. And this is the outcome of our regression analysis, interpreted in terms of the visual illustration that I showed you, and resulting in the conclusion that x is a statistically significant predictor of y with a slope of 2.27 and a p-value of 0.001. Let us now apply this to the situation of vocabulary predicted by age. If we run a regression analysis on these variables, we come up with this result. In this result, we have an estimate of intercept at 8.35. This is its standard error. If we divide the intercept by its own standard error, this is the t-value, and the corresponding p-value is 0.008, which indicates a statistically significant intercept. The intercept is not 0. We don't care about that. What does intercept equal to 8.35 mean? The intercept is our predicted value of the independent variable when the independent variable is equal to 0. So this means that for a child with age equal to 0 months, we predict a vocabulary score of 8.35. This is a very silly thing to say, and it is because the relationship between age and vocabulary is not linear all the way to 0. However, for the statistical analysis, these are just numbers. So we always get an intercept because we need to define the regression line. In practice, this means that we should not be interpreting the regression outside the range of our data. However, it is still the case that this is what the intercept means. This means that at age equals 0, the predicted value of vocabulary is 8.35. So we should not be using this regression line to predict vocabulary at age equals 0. Now moving on to the slope, which is 1.08. Its standard error is 0.04. There's a big t value, which is the ratio of those two, and a very low p-value. So we have a highly significant slope for predicting vocabulary from age. And what this number means is the predicted increase in vocabulary for an increase of age equal to 1 month. What this says, in other words, is that our regression model predicts 1 point higher vocabulary, actually 1.08, for each month of age. This is our predicted slope of vocabulary increase by age. For each extra month of age, we predict an extra 1.08 points in vocabulary. How does this work with actual prediction? Let's bring back our formula. This is the simple linear regression formula, and we need to substitute the values that were estimated in the analysis. So 8.35 will go into the intercept, 1.08 will go into the slope, and our formula for these specific variables becomes like this. Estimated vocabulary equals 8.35 plus 1.08 times age. For example, if we want to predict vocabulary for a child at 60 months of age, we multiply 60 by the slope and add the intercept, and that's about 73 points after rounding. Whereas for a child at 80 months of age, multiply these, add this, and our predicted vocabulary will be 94 points. Let's look at these on the graph. So a child around 60 months of age, exactly at 60 months of age, we hit the line of regression at 73. And for a child at 80 months, we hit the line of regression at 94. These are our predicted values of vocabulary. And of course, we will not be predicting perfectly because there are large ranges of performance associated with each age. So children of the same age can differ a lot in their vocabulary. But we are predicting a good deal of the total variability in vocabulary by taking age into account. This is how we can evaluate the success of our regression model. The first way to consider the relationship between these two variables in the context of regression is the correlation. And we can derive the correlation from the slope by multiplying with the ratio of standard deviations. And in this case, the correlation is equal to 0.7. That is a high correlation between vocabulary and age. The second index we can use is the variance accounted for, the proportion of the total variance in vocabulary that is accounted for by age. And that's R square, which in the simple linear regression is equal to the square of the correlation, and that's 0.49. In other words, age accounts for half of the variability in vocabulary scores, for children between the ages of 4 and 8. Age alone accounts for half of the variability. The other half of variability in vocabulary is between participant variability that is unrelated to age. So there are other causes of differences in vocabulary between children. And a final index evaluating the performance of our regression or of our prediction model is the prediction error. And in particular, the index we use is called the root mean squared error, root mean squared error, and is our familiar index that has to do with the error. So this is the residual, the actual value minus the predicted value, multiplied by itself, so square, divided by the number of points, that's the mean, and then the square root, kind of taking back that square, is the root. So root mean squared error corresponds to the root, the mean squared error. And that's about the same as the standard deviation of the residuals. The difference is that for the standard deviation, we would have divided by n minus 1. But for large samples, these two are essentially the same. Before we go on and actually report the results of a regression, we must make sure that the assumptions underlying these calculations are not violated. What are the assumptions that we need to check for regression? First of all, independence. As for all statistical tests, the measurements of one child must not in any way depend on the measurements for any other child. The second assumption is linearity. Linear regression expresses a linear relationship, just like the correlation coefficient, Pearson's R, which is a quantification of a linear relationship. As we saw, the correlation coefficient and the slope are directly related by the ratio of the standard deviations. So they refer to the same thing, and that's the linear relationship between the variables. So this kind of regression cannot be used with variables that are not in a linear relationship. The third assumption is called homoscedasticity. And that's a long and difficult word, and all it means is that the residual variance should be about the same across the whole range. An easier way to think about this is in terms of the success of our prediction. The idea is that across the whole range of our independent variable x, we should be equally good or equally bad in predicting the dependent variable. We should have about the same dispersion in the residuals. We shouldn't have very large residuals for some values of x and small residuals for other values. The regression is not valid if residuals, for example, are very small in small values of x and large in large values of x, or any other combination. This should be about the same. This should be evenly distributed. And finally, and very importantly, the residuals should be normally distributed. This is a fundamental assumption for regression to hold and be validly interpretable. And this is, in fact, the first thing we should always check even before we look at the results in terms of the estimates for the statistics. The first thing we go and look at is the distribution of the residuals. For this particular analysis, we see that the residuals are somewhat skewed, but this doesn't look too bad, so we can probably accept this analysis. And then we have to look at homoscedasticity, which can be seen as the variance of the residuals across the independent variable. And as we see, the band of residuals is about equally wide. We don't have a small dispersion here and a large dispersion here, or vice versa, and we don't have any strange shapes. Of course, these are noisy, but they are approximately evenly distributed. Usually, this is not the graph that is provided by the statistics programs. Instead, we get a standardized residual plotted against the standardized prediction. And as you can see, these two scatter plots are identical. And that's because, first of all, the prediction is linearly related to the independent variable, so that doesn't change anything. And second, if you standardize variables, the relationship stays the same. So the actual scatter plot that we get out of regression analyses is in fact the standardized residual against the standardized prediction. And the reason we get this one is that this generalizes immediately to cases where you have more than one independent variable. So we need to check these graphs before we move on to look at the results of our analysis. And all of this was just about the simple linear regression with one independent variable. But in general, regression generalizes to much more complicated cases. Most immediately, the multiple linear regression version is one in which we can have more than one independent variable. So we can have more predictors for one dependent variable. And in that case, the slope of each predictor corresponds to the predicted change for an increase in one unit of that predictor. So the meaning of the slope is always the same, but when you have multiple predictors, the slope is the change in the predicted value of the dependent variable when this particular independent variable increases by one and all the other independent variables remain constant. So the slope of each variable is only meaningful by assuming that all the other predictors are unchanged. A statistically significant slope implies that there is an association between this predictor and the dependent variable that is important even after taking all the other predictors into account. So a statistically significant slope in a multiple regression is not the same as a statistically significant correlation. It is possible to have a statistically significant correlation if you only look at this variable, this predictor, and the dependent variable, but not a statistically significant slope if the variability in the dependent variable is already accounted for by other variables. And finally, what we can do with multiple regression is entering each predictor in steps. So run the analysis with some predictor, then add another predictor and study the change and so on. That is called hierarchical multiple regression. And we do this often in order to study how much extra variance in the dependent variable we can account for by the newly entered independent variables, by the new predictors. There are many ways in which regression can be generalized, and in fact, regression is the most useful of all our statistical analyses. And increasingly, all kinds of analyses are recast as regressions. So you're very likely to see regressions either in your own work or in studies by others that you will have to read. It is important to understand the concept of prediction, the concept of slope and residual, and then to be able and generalize these ideas from the simple linear regression, where everything is easy to see and to calculate, to the more complex cases involving many more variables, where you only have the statistical table to interpret.